Okay, any general questions, problems, anything? I did send an email yesterday about the Avogadro project. There is now aluminum foil outside my office. I will also post hours when I will be in my office. Should you need any measurement device I might happen to have in my office. You can, of course, also take the aluminum foil to lab and use the things there as you try to sort through this. I did change the due date on it, so it's no longer due the 8th, it's due the following week. So you should have some time. If you have questions once you've looked at it, give us a holler. Any other issues? Then onward and upward. We were talking about isotopes. Again, in some sense, this is the biggest correction to Dalton's theory. There are atoms that have different masses. Of course, he couldn't see this because he was never able to isolate a single atom to look, right? And so normally, if you've got a sample of any element, it has the naturally occurring mixture of the isotopes. And so on average, they all look like they weigh the same, right? It's purely statistical. You've got trillions and trillions and trillions and trillions of atoms. Unless you make some effort to separate one isotope from the other, you're always going to have the same mixture of isotopes. And so they look like they all weigh the same, but in fact they don't. And so just to be clear on symbolism here, right? If I have the mass number, which is this top number out front, added to my atomic symbol, I am specifying that I only have atoms of that specific isotope. If there is no mass number there, like on the bottom, right, then I am stating, or at least tacitly implying, that I have the naturally occurring mixture of all the isotopes, right? So C+1 at the bottom is an ion of carbon that has carbon-12, carbon-13, and carbon-14 in the naturally occurring statistical ratio, okay? And so again, the nomenclature in some ways is an indirect way of telling you what the number of subatomic particles are, right? So here's good old barium. It's specifically a barium 2+ ion. So again, the top number is the mass number, which again is not the mass of anything, right? This is the atomic number, which of course is redundant with the symbol. And then this is the charge, right? What that's really telling you is the number of protons, neutrons, and electrons, albeit in somewhat indirect fashion, right? And so the only thing it directly tells you is the number of protons, because the atomic number from the periodic table is the number of protons. You can infer the number of neutrons and the number of electrons from the mass number and the charge, right? Because the mass number, I'm going to run out of space here. Is the number of protons plus the number of neutrons. So implicitly, if I have 139 total particles and 56 of them are protons, that is telling me the number of neutrons. All right, 139 minus 56, or 83. And similarly, right, the charge is indirectly telling me the number of electrons, right? Because the number of protons minus the number of electrons has to equal the charge. Because the protons and electrons have exactly the same magnitude charge, just opposite signs. So protons have a positive charge, electrons have an exactly equal negative charge, and so the net charge is just the difference in the number. So again, since I know the number of protons is the atomic number, right, implicitly the number of electrons has to be 54. All right. And so my isotope symbolism is really just specifying the number of subatomic particles. For the most part in here, right, we really only care about the number of protons because that tells us the identity of the elements, and the charge, because as you will eventually see when we actually get to doing a real honest-to-goodness chemical reaction, charge is an issue in how the atoms interact to form molecules. The neutrons, for most of what we do this semester, are irrelevant, right? They matter in terms of isotope mass. They will matter in terms of radioactivity next semester. But for the most part, they're just around for the ride, providing mass, but not doing anything typically useful. All right. And so a lot of this information is coded in the periodic table, so finding your way around the periodic table becomes useful, right? Again, first and foremost, I have my proton numbers, also called atomic numbers, as the way I have actually ordered my elements. So hydrogen is atomic number 1 because it has 1 proton. Helium is atomic number 2 because it has 2 protons. Right, and so I always know the number of protons if I can just find my element in the periodic table. I also have, of course, the symbols, and in most periodic tables, the names. And so, generally speaking, not necessary to memorize such things. It is all coded in there. The other thing I have in there that we'll talk about in a second is the mass, right? The number at the bottom, the decimal number at the bottom, is in fact the mass. Right. As you will see in a second, a little bit of foreshadowing. That, of course, is the average mass of all the isotopes. And as I'm somewhat fond of saying, in fact, the atomic mass is not the mass of any atom on the planet. Right? There is no carbon atom that weighs 12.011 anythings anywhere. Right? It's the statistical average mass. Right? If you want a perfectly good analogy, the average family has 2.2 children. I defy you to find any family in America that has exactly 2.2 children. All right. Well, I guess there's probably a serial killer family somewhere hasn't finished eating the 3rd child. Right? Fundamentally, when I take the average, I have a statistical average of everything, but none of them actually match that. Right? The other thing that we'll talk about more in the next week or so is the structure of the periodic table is arranged around electron configuration because the electrons do all the chemistry, right? And so the other thing worth noting about the periodic table is the way different types of atoms are grouped, right? And so everything that's currently in gold on the screen is termed a metal because it is to the left of what on many periodic tables is usually an extra bold line that follows this stair pattern. And that handful of elements in the upper right-hand corner are termed nonmetals. Metals have certain properties in common, as do nonmetals. And so they represent families of elements. In fact, of course, they're not all identical. And so it's not a completely binary distinction. And so as you get close to the boundary line, right, the elements that are along that boundary have some properties of the metals and some properties of the nonmetals. And so to that end, they are sometimes referred to as metalloids or semi-metals. Right. That makes the chemistry of many of them interesting, but also a little complicated, because sometimes they behave like metals and sometimes they behave like nonmetals. Right. The other families worth noting are the columns in the periodic table, as again we will see in the next week or so, right? Because electrons do the chemistry of the atoms, right? The periodic table is actually arranged in terms of similar electron structure families in columns. And so the first column in the periodic table, because they have similar electron configurations, have similar chemical behavior. And so they are considered a chemical family. Right? And so that first column is frequently referred to as alkali metals, for a reason that becomes more obvious in spring. Right? But they all behave similarly chemically. And so they are a chemical reactive family. Right? In the usual somewhat confusing fashion, because I'm not in charge of naming things. Right? The second column from the left are known as alkali earth metals. Right? And again, same issue. They're in the same column in the periodic table. They have similar electron configurations. They have similar chemical behavior. Right? We'll skip to the other end for a minute. Right? The last column in the periodic table is both the most interesting and the most boring chemical family on the periodic table. Right? They are known as noble gases. Right? I say they are both most interesting and most boring. They are noble gases because they are not very reactive. And so they tend to be chemically inert and not do a whole lot. Right? On the other hand, when they do something, it's kind of bizarre, unusual, and interesting. As you will see when we get to atomic structure, right? If I start moving right to left, the second to last column are called halogens. And again, they are all, generally speaking, chemically similar, right? In these columns now, I really have to truncate my columns because I have, you know, my stair-step separation between the metals and the non-metals here. And so the ones at the bottom here are now actually metals, or at least metalloids. And so they are not quite as chemically identical as the things at the top of the column. And so I'm going to cut my oxygen family short. All right. But oxygen, sulfur, selenium, and tellurium are known as chalcogenides. Right. The name less important than the fact that they are chemically similar. Right. The group in the middle, which I skipped over for now, are known as transition metals. They have interesting and varied chemistry. We talk a lot more about them in the spring. We will talk a little bit about them here. Right. And we will come back to those families in the next week or so when we talk about electron configurations. For now, I'm still somewhat obsessed with mass. Right. And I promised at some point we would forever dispense with AMUs. It is coming, right? Remember, my isotopes, right, are defined by mass number, which is technically not the mass of anything, right? The one that was actually equal to the mass was carbon-12. By definition, and totally arbitrary definition, carbon's mass, carbon-12's mass, was set at 12 AMUs. Right. And then again, everything was measured relative to that. Right. But still in this rather nebulous, ill-defined, and hard to measure AMU. And so I would prefer to have something I could actually measure, right? Which we will get to very, very shortly. I mentioned earlier, right, that the periodic table says the mass of carbon is 12.011. That is the statistical average of the 12s, the 13s, and the 14s. Right. It is a weighted average. Right. And so, I don't know. Your first years, maybe you don't calculate GPAs. By the time you're fourth year, everybody knows how to calculate their GPA. But a weighted average is just what it sounds like. It weights the individual entries by how much they count in the overall sample. So for example, if you're polling, right, it's basic polling sampling technique, right? The country is 52% women or something like that. So if you're going to take a poll to try to represent the country, you have to make sure it's 52% women, right? And so women count for slightly more than men. Some of you would say they count for a lot more than men. Shame on you, right? But in any sample, you have to weight it by how many people are in the population. That's all that's really going on here. In terms of GPA, right, courses count differently. So if you're taking, well, this is an old slide. We're not 4 credits anymore. But, you know, if your chemistry lecture is 4 credits and your chemistry lab is 1 credit, when you go to calculate your GPA, the 4 credit hour course has a lot more impact than the 1 credit hour course, right? And so if you take an atom like neon, which has 3 isotopes, right? There's neon 20, which has a mass of 19.9924 AMUs. Right. There's neon 21, which has a mass of 20.9938 AMUs. And there's neon 22, which has a mass of 21.9914 AMUs. Right. Again, the only isotope in the entire periodic table, right, is carbon-12 that actually has a integer mass. Right. Now, if you were to average those as they are, you would get something around neon 21. Right. But they are nowhere near equally common. And so we have what's known as natural abundance. Right. This is the percent of each known to exist in nature. And again, if I have a sample that's large enough, right, I should always have the statistical mix of the isotopes. And so the natural abundance of neon, as you can see, is very, very heavily weighted towards neon 20. Right. Slightly more than 90% of all neon atoms in the universe, presumably. Since we haven't left the planet, you can't know for sure, but theory says they should be evenly distributed through the universe. Right. Slightly more than 90% of all neon atoms in the universe are neon 20. Most of the rest of them are actually neon 22, a little over 9%. Right. And a measly 0.27% of neon atoms are actually neon 21. Right. As a result, the average mass of neon isotopes is very close to neon 20, because that represents more than 90% of all neon isotopes. And so my weighted average for the isotopes has to take into account both the mass of each isotope and the relative number. And so there's two ways I can do this. I either take the mass of each and multiply it by the fraction. So I turn my percent into a fraction. 90.48% is 0.9048 as a fraction. All right. And my 0.27% is 0.0027 as a fraction. And if I add them all up, I get 20.180 AMUs as the statistically weighted average of all the isotopes. Right. I will stand here and count to myself for a second to let anyone who's writing that down catch up before I show you, foreshadowing for those of you not writing or done writing. That is the number you see in the periodic table. Right. And that's why I say, right, the number you see in the periodic table is the average of everything, but it really isn't anything. If you had a single atom of neon, it has to be either 19.99 AMUs or 20.99 AMUs or 21.99 AMUs, because those are the three isotopes. It can't be 20.18 AMUs, right? Because no isotope actually has that mass. But if you average, right, hundreds or thousands or however many atoms you think you need to get a statistically significant sample, right, you get an average mass of 20.18. This periodic table, I don't know if you can see that, has one more sig fig, right, 1797, which of course rounds to 20.180, right? And so my atomic mass in the periodic table is the statistical average of all the isotopes, right? But that is actually more useful to me than the actual masses of the isotopes, because 99.999% of the time, I am dealing with a random mixture. The only time I have single isotopes is if I go out of my way to isolate them. And there are times you would do that, right? If you want to label something isotopically with something radioactive, you want to isolate the radioactive isotope and use only that. If you're trying to build an atom bomb, you only want the explosive isotope of uranium, not the inert isotopes of uranium. But that requires a lot of effort and is sometimes very, very difficult. And so 99.999% of the time, I am not caring about the isotope. I am just trying to make a molecule. I don't care if there's a couple molecules with slightly different masses, because they have slightly different isotopes in them. And so if I scoop up a sample of carbon, right, it's going to have an average mass of 12.011 AMUs still for the next 5 minutes, right? Even though none of the atoms in there have that mass, right? The other way you could have calculated that, just, you know, FYI for math, right? If I use the percent instead of the fraction, I could multiply the isotope mass by the percent natural abundance and then divide by 100 at the end. I just essentially divided by the 100 earlier. Right. And of course, when you go to Sheg, and I know you do, or any place else on the internet, they might do it either way, depending on who did it. But it is, of course, mathematically equivalent. Yes, no, maybe. right? And of course, if I build molecules from atoms, right, I'm really just adding the masses, right? With the same basic caveat, what I'm going to end up with is a statistically average mass of all the combinations, because if I add neon to oxygen, right, it's going to be neon 20, 21, or 22. It's going to be oxygen 15 or 16. There's going to be a bunch of molecules that have different isotope masses, but the average of all of them, because there's so many, should always be the same, right? It's worth pointing out the one group to sort of be aware of, and this came up last week, are the diatomic elements. These are technically molecules, not atoms, of course, but they are the elemental form of that particular species. So if I have a sample of oxygen, it is never O. It's always O2. O by itself, not really stable, right? And there's 7 of them. And again, my mnemonic for remembering them is halogens Hun, right? The first 4 halogens plus hydrogen, oxygen, and nitrogen. At some point, I will say that to like 10 of you, and 3 of you will give me a strange look. Happens every year, right? But remember it however you want, right? But if I say, you know, that we're doing a reaction with hydrogen and oxygen, it is always H2 and O2, as that is the elemental form, right? You can, of course, also form diatomic molecules from different species, right? Diatomic simply means 2 atoms. In that case, the masses add. This is, again, where it is helpful to have a mental picture of the molecules as physical objects as opposed to just symbols. And so, again, however you want to think of it, right? MgO is just an Mg stuck to an O, right? And if you think of it that way, it makes perfectly good sense how you get the total mass, because if I was going to weigh an Mg and an O, right? If I throw them on the scale, I just get the mass of both of them. There is no fancy way of mixing them. The masses just add up, right? And so a molecule has a quote unquote molecular mass, just like an atomic mass, right? The only thing I still currently hate about this is I'm still talking AMUs. And so I would like to now dispense with AMUs forevermore, because again, I don't have a scale that measures anything in AMUs. I would prefer to weigh something in a more common mass unit like grams, right? Which I can do if I just figure out how an AMU is related to a gram, right? And so if I have MgO, I'm really just going to add the Mg to the O, right? And so here's good old Mg with, again, an average isotope mass of 24.305. Here's good old O with an average isotope mass of 15.9994. Right, that means, right, the average, well, I seem to be missing a slide, right? That means the actual mass of MgO is 40.304-ish. Again, technically still in AMUs, because I haven't tried to marry the AMU to something more useful. Right. And the last few slides of this presentation are actually redundant with the first few slides of the next presentation. So not to confuse you, I'm going to skip over to the next presentation. Why is that stuck? There we go. When we were talking about measurement way back in week 1, I said, you know, you would never measure the width of the human hair in kilometers. It's too big a unit. All right. You would never measure the size of a planet in millimeters. It's too small a unit, right? That's really the gram issue with molecules and atoms. Grams is way too big a unit to measure a single atom, right? The solution to my problem is to never measure a single atom. I just want to group them. If you'd like the everyday, you know, shopping metaphor, right? You don't go to Wegmans or any other grocery store and buy sugar by the grain. You buy a 5-pound bag of sugar and you're done. How many grains are in there? Depends on what each grain weighs. That's really the mole issue, right? A mole is really just a collection designed to be big enough so that grams make sense as a measurement unit, right? So technically speaking, the entire periodic table was initially constructed using AMUs because nobody knew how big an individual atom was. And frankly, if I were to use the grams for an individual atom of hydrogen, it is tiny. It's 10 to the minus 27 grams approximately, right? And so originally these were all AMUs. If I'm going to make them into something useful like grams, what I need is a big collection of them that now weighs grams. That is all Avogadro's number represents. It has no great significance, even though it is a very exact looking number with a whole lot of sig figs to it that people spend a whole lot of time measuring, right? But the whole purpose of Avogadro's number is to be a collection of atoms or molecules that now has a gram size weight, right? So technically, the mass of carbon was originally determined to be AMUs in a very arbitrary way. Carbon 12 was called 12, everything was weighed relative to it, and then we averaged all the isotopes. Right. Since my scale is in grams, AMUs is a dumb unit. So what I'm going to do is simply collect a whole bunch of atoms until I have 12.011 grams of carbon. Right. You can find this to about 8 or 9 significant figures if you care. Right. Avogadro's number, again, has no real significance. It's not some kind of universal constant of nature. Right. But if you take 6.022 times 10 to the 23rd atoms, right, each of which weighs 12.011 AMUs, the 6.022 times 10 to the 23rd carbon atoms will weigh 12.011 grams. Right. And grams is a much better unit because let's face it, all of my scales are calibrated in grams, not AMUs. Right. This particle collection is referred to as a mole. It is really just our favorite unit, which is why if I don't drive you nearly insane by saying units, I will drive you fully insane by saying moles just as many times. All right. Mole is a very, very chemical unit. You don't see it anywhere else in science, usually. Right? But everything chemists do are in terms of moles. And it is really just a grouping. It is no different than a dozen. Right? A dozen is just 12. I went and bought donuts. I asked for a dozen. They gave me 12. And yes, before some smart aleck says it, baker's dozen, 13. Right? A gross is technically a dozen dozens, 144. I can buy a gross of something. And if I say gross, they give me 144 because everybody knows there's 144 in a gross. 500 is a ream, mostly used for paper. I buy, usually, if you want to drive them crazy at Staples, go ask to buy a single sheet of paper, see what they say. Right? It comes pre-packaged in reams. Why? That's an office-sized collection. Why do eggs come in a dozen? That is a kitchen-sized collection. Right? A mole is just a laboratory-sized collection of atoms. Because they're really, really small and really, really light, it takes more of them, right, to be room-sized. How many more? 6.022 times 10 to the 23rd, right? All a mole is a way of counting in groups. Right? I have 10 moles of carbon. Technically, that means I have 6 times 10 to the 24th carbon atoms. But I don't ever have to say that. Right? Just like with the donuts, I can tell you I bought 3 dozen. I don't have to turn that into 36. You may not even in your mind turn that into 36 because things that get counted in dozens, we're used to just counting them in dozens. I went and bought a dozen eggs. Right? If your mother ever sent you to the store, did she ever tell you get 48 eggs? Right? She says get 4 dozen. You probably don't even bother to think that that's 48. You pick up 4 cartons, each of which has a dozen. Right? I'm doing the same thing with mole. And I make a big point about this because technically speaking, we never use Avogadro's number to get to moles, except as a strictly academic exercise in this class for like today. Or, you know, maybe on the first exam. Because my atoms or molecules always come in mole-sized packages. I don't need to unpack them. Right? And so moles is just my unit for counting individual atoms. Right? It is helpful, right, in terms of giving me a way to weigh them. And that is helpful because weighing things is cheap and easy and accurate. Right? But in the end, it's just a room-sized calculation. Right? And the reason I care to count them is because my chemistry is fundamentally about counting. Right? Here's a chemical reaction. In some sense, virtually our first chemical reaction of the entire year. Only took us 2.5 weeks to get there. Oh no, we started on a Wednesday. Took us exactly 2 weeks to get there. All right. If I take magnesium and oxygen, I can make magnesium oxide, which is what MgO is called. All right. What that chemical reaction really is a recipe to make magnesium oxide. And the recipe is written in individual particles. right? What that really tells me is, right, get two magnesiums, whoops, and one oxygen, which of course is diatomic, so it's actually two oxygen atoms, and rearrange the atoms so that each magnesium is attached to one oxygen. Right? Chemical reactions are fundamentally about numbers of particles. That's why I said Monday. It's really Legos. All I've done is rearrange my Legos. I stuck an oxygen Lego on a magnesium Lego and I made magnesium oxide. That recipe does not care what they weigh. That recipe does not care how big they are, volume-wise. It doesn't care what color they are. It doesn't really care what shape they are. It cares how many there are. And so if I'm going to do that recipe, right, I need two magnesium atoms for every one oxygen atom, and I will get two magnesium oxide molecules, right? That is what my balanced equation up here is telling me. I need two of these. Implicitly, there's a 1 here, and I get 2 of those. Right? It's really a counting issue. But again, if you want to count out a room-size sample of magnesium, you won't live long enough. Right? If you're bored some night this week, try to count to 1,000,000 and see how long it takes. Because to count to 10 to the 23rd, right, is a million, millions. Or it's a billion billions. Try to count to 1,000,000,000 someday. You can do the math. If you counted one number per second, how long does it take to get to 1,000,000,000? Right? To actually count them would be difficult, but I don't have to count them because I know what they weigh on average. And so if I weigh them, I can correlate the mass to the number, right? And that's where my moles, right, is useful as a way of turning AMUs into something more useful. Avogadro's number of particles weighs in grams what the individual atoms weigh in AMUs. But that's a far more useful number because I don't do my chemistry with a single atom usually. It's very expensive and hard to do. I usually have a room-sized quantity. And if I take a scoop of sugar, right, it's around a mole. A mole of sugar is like 4 ounces. It's a room-sized quantity of sugar. But when I go to react the sugar with something else, it doesn't care what it weighs. It cares how many individual molecules there are, right? And so, forever dispensing with AMUs for something more useful, right? If I have a mole of particles, my AMUs become grams. And grams is easy to measure. And so now my atomic masses or my molecular masses, if I've combined my atoms into a molecule, aren't actually masses, they're conversion factors, right? Because the way I want to interpret these numbers in the periodic table forevermore is not as AMUs, it's not as individual atom masses, but it is as the mass of a useful group of atoms. And so carbon is not 12.011 AMUs anymore. That would be the mass in very arbitrary units of a single carbon atom. Right? But I am going to group my carbon atoms into a mole of carbon atoms. Right? And so this number is not AMUs anymore. I'm going to, just to make myself feel better, cross it out. Because I now want to measure not an individual atom, but a whole mole of atoms. Because a mole of carbon atoms weighs 12 grams. 12 grams is about 1/3 of an ounce, a little over, right? That's a room-size amount of carbon, right? That's something I can take my spatula, scoop out of a container, and throw in a beaker and do something with. Right? And my mole of carbon weighs 12.011 grams. And so my atomic mass now has more useful units, grams, but it is also a compound unit. It's grams per mole, right? Anything with compound units is fundamentally a conversion factor. Right. So my atomic masses are now conversion factors between the mass of something that is easy to measure and the number of particles, which is what I care about when I do the chemistry, right? My reaction is written in terms of number of particles, not mass. There is nothing in that balanced equation that tells me anything about the mass. It doesn't care about the mass. I mean, sure, on a physical sense it does, but in my recipe it does not. It is the picture at the bottom. 2 individual magnesium atoms will react with 1 oxygen molecule, which has 2 individual oxygen atoms, to make 2 magnesium oxide molecules, each of which has 1 magnesium and 1 oxygen. Right? My chemistry cares about number of atoms. That is hard to determine because there's so many of them and they're so small. But grams is easy to measure, throw it on a scale. Right. And so my molar masses are the perfect conversion factor for doing real practical chemistry in a lab. My grams is an easy to measure unit. Moles, again, remember, is just a group, a number of particles, which is the only thing the chemistry cares about. How many magnesium atoms do I have? Right? And so this is just another conversion factor. It happens to be the most common, and I might argue most useful, chemical conversion factor, because it allows me to count atoms with a scale. Because again, I know what the average mass of my atoms is, right? So if I throw my carbon on a scale and it weighs 36.0 grams, that's great, that's useful, that's the number, put it in your lab notebook. But when I now go to do my chemistry with carbon, what I care about is how many actual carbon atoms there are, right? And so from the periodic table, the atomic mass of carbon is 12.011, no units in the periodic table. But from this moment forward, the unit I put with that should be grams per mole, banishing AMUs to the dust heap of history, at least until you go on the internet and somebody else uses them. All right. And so again, the periodic table says 12.011 for carbon. I immediately slap the units grams per mole on there, which makes it a conversion factor because it has compound units. How I use that conversion factor just depends on what I'm trying to cancel and what I'm trying to create. I have grams, I want moles, right? So again, from the periodic table, I've got that, but I need the grams to be in the denominator to cancel the grams of carbon. So I flip my conversion factor upside down, and that gives me moles of carbon. All right. And I don't need to do any more. The other thing that people commonly want to do is, hey, if I say how many carbon atoms, you want to throw Avogadro's number in there. There is no need. Mole is number, right? It's the same as if I say how many eggs did you buy, you say 4 dozen. You don't have to tell me 48. Right? So again, I threw Avogadro's number up there and I told you what it means. We hardly ever use it because it's okay to count in moles. I have 3 moles of carbon there. If I'm now going to react it with something, I'm going to react it with 3 moles of oxygen or 10 moles of oxygen, right? And so, you know, it's another one of those purely chemical things that you sort of have to add to your lexicon, right? Mole is just number, it's a way of counting. If you get used to thinking of moles that way, it's much easier, right? Because it is kind of a foreign unit that gets used almost nowhere but chemistry. Questions or problems? We will practice some things with that on Friday. Questions, issues, anything? Then happy September, since it's the first time I've seen you in September. Have a good day. I will see some of you on Friday.